on multicollinearity, and today we will learn what is multicollinearity and the effects of multicollinearity or the problems due to multicollinearity. So, what is multicollinearity? What is multicollinearity? Okay. The problem of multicollinearity exists when two or more regressors variable are strongly correlated or linearly dependent. Okay, suppose we wish to fit the model y equal to x beta plus epsilon. So, we are assuming that we are considering that there are this is the matrix form of multiple linear regression, and there are k minus 1 regressors and 1 response variable. Okay. So, we know that the least square estimates of beta is beta hat equal to x prime x inverse x prime y. Okay. So, now if x prime x is singular, then we can't perform the inverse x prime x inverse. Okay. And singular means the determinant is equal to 0, x prime x determinant is equal to 0, and this happens when at least one column of x is linearly dependent on the other columns. Okay. So, that means the columns of the ith column of this matrix X stands for the ith regressor variable. So, the meaning of this one is that if one regressor can be one regressor is linearly dependent on the other regressors, then x prime x is singular, and we can't compute the inverse of the x prime x matrix. Okay. Let me give one example for this one. uh, an example. Can we use the data below to get a unique fit to the model y equal to beta naught plus beta 1 x 1 plus beta 2 x 2 plus beta 3 x 3 plus epsilon. Okay, and the data, here is the data x 1, x 2, x 3 and the response variable y. So, 1 minus 2 4 81, 2 minus 7 11 88, 4 3 5 94, 7 1 13 95, 8 minus 1 17 123. So, here in this example we have 3 regressor variables x 1, x 2, x 3 and one response variable, and here is the data. Now, the question is whether we can use the data, use this data to get a unique fit to this model. Well, of course, we can get a unique fit, that means we can estimate the regression coefficients using the least square estimate, that is beta hat equal to x prime x inverse x prime y, provided provided x prime x is not singular. Now, here if you observe, it is not difficult to check that these 3 regressors are not independent. Here you check that x 2 plus x 3, take this first observation. So, x 2 value is minus 2, x 3 value is 4 and x 1 value is equal to 1. You can check that x 2 plus x 3, that is equal to 2. So, x 2 plus x 3 is twice of x 1. Take the second observation, x 2 plus x 3 is equal to 4, which is 2 times of x 1. Third observation also, x 2 plus x 3 equal to 8, which is 2 x 1. Okay. So, here the relation between the regressors is like x 2 plus x 3 is equal to twice x 1, or same as writing that x 1 can be expressed in terms of using x 1 depends on x 2 and x 3. So, x 1 is x 2 by 2 plus x 3 by 2. Okay. So, here really we can't estimate the regression coefficients, because x prime x is singular here. So, here because of this fact they are not independent on. So, that is why x prime x is singular. So, x prime x determinant is here, it is exactly equal to 0, determinant is equal to 0. Okay. So, this is an example here which illustrate the definition of multicollinearity. Here I mean in this problem, I mean in this particular data the problem of multicollinearity exists because the columns of x. So, the x is nothing but the, the x matrix is nothing but this one. So, here the one column, for example, the first column can be I mean it's linearly depend can be written as the linear combination of x 2 and x 3. So, that is why x prime x is singular, and the problem of collinearity exists here. Okay. So, next we will be talking about the effect of multicollinearity. Multicollinearity. Well, the first or I can also say that the problems due to multicollinearity. So, the first one is it says the strong multicollinearity between regressors results in large variance and covariance of regression coefficients. Okay. So, now I am going to illustrate what I mean by this. This says that if there exists a strong multicollinearity in the data, then that results in large variance and covariance of regression coefficients. Okay. So, let me consider multiple linear regression model with two regressors. Right. So, my model here is y I equal to beta naught plus beta 1 x I 1 plus beta 2 x I 2 plus epsilon I. So, this I stands for the ith observation. So, I is from 1 to n. Now, the X matrix for this fit consists of the columns So, here is the X matrix. X matrix for this model is we know that this is 1 x 1 1 x 1 2 right 1 x2 1, x2 2 like that 1, xn 1, xn 2. Okay. Now, we will talk about the centering and scaling of this regression data. Centering and scaling of regression data. So, what we do is that if we replace, if we write x I 1 is equal to x I 1 minus x 1 bar by S 1 1 square root of that. So, let me tell what is this notation. X 1 bar, of course, it is the mean associated with the first regressor. So, this is equal to 1 by n summation x I 1, I equal to 1 to n, and S 1 1 is equal to summation x I 1 minus x 1 bar square sum over I equal to 1 to n. Okay. So, well, let me write also, say x small x I 2 equal to capital X I 2 minus x 2 bar by S 2 2 square root, and y I small y I is equal to capital Y I minus y bar by root S y y. Okay. So, this is the mean associated with the second regressor. So, x 2 bar is equal to 1 by n summation x I 2, I is from 1 to n, and S 2 2 is equal to x I 2 minus x 2 bar whole square 1 to n, and here also y bar is equal to summation y I 1 to n, right, and S y y is equal to summation y I minus y bar whole square. Okay. So, what I did here is that my original data is x 1, x 2 and y, and then what I am doing is that I am replacing this x 1 by small x 1. So, small x 1, small x 2, just notation only, and then small y. Now, one thing we need to observe is that the mean of the original observation is I mean the mean associated with the first regressor for the given data is of course it is always x 1 bar. Well, but here if you take the mean of the transformed data, now this the mean of small xi is 1 is always equal to 0. So, here x 1 bar is equal to 0, similarly x 2 bar is also equal to 0 and y bar is also equal to 0. And the other thing to observe here is that summation x I 1 square 1 to n, this is equal to 1, this is equal to 1, and this is also true for the second regressor like summation x I 2 square 1 to n is equal to 1 and summation y I square 1 to n is equal to 1. Okay. Now, the model for the original data is we wanted to fit this model y equal to beta naught plus beta 1 x 1 plus beta 2 x 2 plus epsilon. Well, this transformation is called centering and scaling of regression data. And here for this model we know that the least square estimates gives beta naught hat is equal to y bar minus beta 1 hat x 1 bar minus beta 2 hat x 2 bar, right. But if you feed the same model here for the transformed data also, if you feed the model like y equal to beta naught plus beta 1 x 1 plus beta 2 x 2 plus epsilon for the transformed data, I am fitting the same model, then it is not difficult to check that beta naught hat is going to be 0 here, because see beta naught hat is equal to y bar minus beta 1 hat x 1 bar minus beta 2 hat x 2 bar. But all this y bar is equal to 0, x bar is equal to 0, x 1 bar is equal to 0 and x 2 bar is also equal to 0. So, here this intercept for this transform data is always going to be equal to 0. So, that is why for this for this scaled and centered data we will omit the intercept beta naught from the model. So, the model assuming that x 1, x 2 and y are centered and scaled is just y I equal to beta 1 x I 1 plus beta 2 x I 2 plus epsilon. I. So, we omitted the intercept beta naught from the model, because for the centered or the scaled data, we just checked that intercept beta naught is always going to be equal to 0. Well, so now next we will write down the X matrix for this model. So, the X matrix is equal to basically it is x 1 1, x 1 2. I am writing small, that means this is the transformed for the transformed data, x 2 1, x 2 2 and x n 1, x n 2. See that column 1 1 1 1 is not there, that column is associated with the intercept beta naught. Okay. So, this one is basically x 1 1 is nothing but x 1 1 minus x 1 bar by root of s 1 1. X 1 2 is x 1 2, capital X 1 2 minus x 2 bar by root of s 2 2, and similarly x 2 1 minus x 1 bar by root of s 1 1, x 2 2 minus x 2 bar s 2 2, and we have x n 1 minus x 1 bar by root of s 1 1, x n 2 minus x 2 bar by root over of s 2 2. Okay, so, this is the X matrix for the transformed data, you can say. Now, what is the normal equation associated with this model? The normal equation in general basically I am trying to find the least square estimate of two regression coefficients beta 1 and beta 2. So, the normal equation is x prime x beta hat equal to x prime y. Okay, you know what is y? Y is in matrix form, y equal to y 1 1 minus y 1 y equal to capital Y 1 minus y bar by root of s y y, y 2 minus y bar by root over of s y y. Similarly, y n minus y bar by root over of s y y. So, this is what the Y matrix is. Okay, so here is the normal equation. Now, what is x prime x? This one is, this implies, see x prime x is, you can check that the x prime x is 1, and then R 1 2. This R 1 2 is nothing but the sample correlation between x1 and x2, okay, and 1 here, because of the fact because of the fact that this sum xi1 square is equal to 1 and sum xi2 square is equal to 1. That is why these two elements are equal to 1, and beta hat here, this matrix beta hat has two elements, beta 1 hat, beta 2 hat, which is equal to R 1 y R 2 y. Well, this R 1 y is the sample correlation between x1 and the response variable y, and R 2 y is the sample correlation between the second regressor and the response variable y, right. So, the normal equation we have is R is 1, R 1 2, R 2 1, R 1 2 and R 2 1 are same 1, beta 1 hat, beta 2 hat is equal to R 1 y, R 2 y, right. Well, where I already mentioned that R 1 y or R 1 2 is sample correlation between x1 and x2, and R 1 y is the sample correlation between x1 and y. Similarly, R 2 y is the sample correlation between x2 and y. So, what is this formula of R 1 y? R 1 y is equal to sum x1 I xi1 minus x1 bar into yi minus y bar 1 to n root over of s11 syy, and R12 is equal to sum x I1 minus x1 bar yi minus y bar. Sorry, this is equal to x I2 minus x2 bar, right, S11 S22. So, maybe more precisely I should replace them by capital X, capital Y. Okay. So, you can check with the original X matrix now. This is the X matrix for the transform data, and then you can check why x prime x is equal to this. You know what is R12 and what is R1y, R2y, all these things. So, you can check that how why this element is R 1 2. That is the sample correlation between the regressor x1 and x2. Okay. Now, to get beta 1 hat and beta 2 hat, we need to compute the inverse of this matrix. This matrix is called the correlation matrix now. Okay. This x prime x matrix, this one is now it is called the correlation matrix. Okay. Well, so what we have is that we have x prime x is equal to 1 r 1 2 r 2 1 1 here, and you can check that the inverse of x prime x is x prime x inverse, which is equal to 1 by 1 minus r 1 2 square minus r 1 2 by 1 minus r 1 2 square minus r 2 1 1 minus r 1 2 square 1 by 1 minus r 1 2 square. It is not difficult to check that this is the inverse of x prime x, right. Well, so beta hat, the least square estimator of the regression coefficient beta hat is equal to x prime x inverse x prime y. Okay, so which is equal to 1 by 1 minus r 1 2 square minus r 1 2 1 minus r 1 2 square minus r 2 1 1 minus r 1 2 square 1 by 1 minus r 1 2 square. X prime x inverse x prime y is equal to r 1 y r 2 y. Okay. So, from here, you know, the estimates are beta 1 hat equal to r 1 y minus r 1 2 r 2 y by 1 minus r 1 2 square, and beta 2 hat. So, this is basically the least square estimate for the transformed data in terms of the correlation coefficient, sample correlation coefficient, and beta 2 hat is r 2 y minus r 2 1 r y r 1 y by 1 minus r 1 2 square, right. So, what I said, the problem with if there is if there is a problem of multicollinearity in the data, then that results in large variance and covariance of regression coefficients. So, right now we have the least square estimator of the regression coefficient beta 1 and beta 2. Next we will check what is the variance of beta 1, and we are going to prove that the variance of beta 1 and also the variance of beta 2 that tends to infinity as r 1 2 tends to 1. That means when there is a strong multicollinearity between the regressor x1 and x2, then the variance of beta 1 hat and the variance of beta 2 hat are going to be infinity. So, that is what we are going to prove now. So, next we need to find the variance of beta 1 hat and variance of beta 2 hat in terms of the sample correlation coefficient R. Okay. So, the variance of, we know that variance of beta j hat in general is equal to sigma square x prime x inverse the jth element of this x prime x inverse, right. So, here from this formula, variance of beta 1 hat is equal to sigma square into x prime x inverse 1/1th element. Okay. So, what is x prime x inverse 1/1th element? The 1/1th element is 1 by 1 minus r 12 square. Okay. So, this one is equal to sigma square by 1 minus r 12 square. Now, if, so this is the variance of beta 1 hat, and similarly the variance of beta 2 hat is equal to sigma square x prime x inverse 2/2th element, which is also equal to 2/2th element is also 1 by 1 minus r 12 square. So, here the variance of beta 2 hat is also sigma square by 1 minus r 12 square. Well, now if there is strong multicollinearity between the regressor x1 and x2, then the correlation coefficient R12 will be large. So, large means the modulus value can be equal to 1. So, when R12, the modulus of R12 tends to 1, the variance of beta 1 hat tends to 0. So, this tends to infinity. So, this tends to infinity as R12 tends to 1. So, this will tends to 1 when the regressor x1 and x2 are strongly correlated, or you can say when there is strong multicollinearity between x1 and x2, then R12 tends to 1. Similarly, this quantity is also the variance of beta 2 also tends to infinity as R12 tends to 1. Okay. So, also I said that strong multicollinearity results in large variance and covariance. So, what is the covariance of beta 1 hat and beta 2 hat? This is equal to sigma square x prime x inverse 1/2th element. Okay. So, what is 1/2th element or 2/1th element? That is minus R12 by 1 minus R12 square. Okay. So, this one is going to be sigma square R12 minus 1 minus R12 square, and this also tends to plus minus infinity depending on whether depending on whether R12 tends to plus 1 or R12 tends to minus 1. So, this is the proof of we using two regressors in the model, in the multiple linear regression model. We illustrated how the strong multicollinearity results in large variance and covariance in of the regressor coefficients. Okay, so the same, so this illustration is using the two regressors in the multiple linear regression model, but this is also true if you have more than two regressors in the model. So, that we are going to mention now. Suppose you have more than two regressors in the multiple linear regression model, then it can be proved that it can be shown that the diagonal elements of x prime x inverse matrix are 1 by 1 minus r j square for all j from 1 to k minus 1. So, I am talking about a multiple linear regression model with k minus 1 regressors, and of course, I need to define what is this rj square. So, here before we had r12 square. Okay. Now, r12 has been replaced by rj, where rj is the coefficient of multiple determination from the regression of xj on the remaining k minus 2 regressors. Okay, I think I need to explain this here. Okay, rj square is the coefficient of multiple determination. We know what is coefficient of multiple determination in multiple linear regression model, that is r square is equal to SS regression by SS total, and this parameter measures the proportion of variability in the response variable that is explained by the regressor variable. But here what I mean by rj square is that so that is we know what is r square, the coefficient of multiple determination, when we fit a regression model between y and the between the response variable and the k minus 1 regressor variables. But here this Rj square is the coefficient of multiple determination from the regression of Xj on the remaining k minus 1 regressors. That means, here the multiple linear regression model is in between Xj and the remaining k minus 1 regressors. So, here Xj you expressed in terms of the remaining regressors, say x1, x2, xj minus 1, xj plus 1, xk minus 1, right. So, here the model is in between, trying to express xj in terms of the remaining regressors. So, if you can recall my first example today, there I told we have checked that the x1, if I am recalling correctly, x1 is equal to x2 by 2 plus x3 by 2, and this one is true for all the observations we had. So this is what we want, and the coefficient of multiple determination for this example, this one is basically R1 square, and here R1 square is 100%, because x2 and x3 can explain 100% of the variability in x1. So, what we do, so this Rj, now I hope you understood that what is Rj square. Rj square is the coefficient of multiple determination for this regression model. So, you feed the model, you express xj in terms of the remaining regressors, and then you compute SS regression for this model, you compute SS total, and you will get Rj square. Well, okay. So, since this is the diagonal element, now I can say that when you have more than 2 regressors in the multiple linear regression model, the variance of beta j hat is equal to sigma square x prime x inverse the jth element, and the jth element is equal to sigma square by 1 minus Rj square. Okay. So, this tends to infinity as Rj square tends to 1. Rj square tends to 1, I mean sometime we write, most of the time we write this in terms of percentage. So, Rj square is 100%, means that Rj square tends to 1. Okay. So, Rj square tends to 1 means this will happen if there is strong multicollinearity between xj and any subset of other k minus 2 regressors. Then Rj square will be close to unity. Okay. So, if there is a strong multicollinearity between the regressor xj and any subset of the other remaining k minus 2 regressors, then Rj square will be close to unity, and the variance of beta j hat will be will tend to infinity. So, this proves, just today we could manage to talk about only one effect of multicollinearity, that means only one problem due to multicollinearity, that says that strong multicollinearity results in large variance and covariance of the regression coefficients. And we illustrated this point both for the multiple linear regression model using 2 regressor variable in the model, and then in general. Well, next class we will be talking about some other, there are several effects of multicollinearity in multiple linear regression model. So, we will be talking about those problems in the next class. Thank you very much.